I'm Adam from RFOXiA, from our real lab. Today we are answering why every BLE device on the market claims a completely different range, and why none of those numbers actually apply to your build. Let's start with what a range claim actually is. When a chip manufacturer prints a number on a data sheet, say 100 meters or 400 meters or 1 kilometer, that number was produced under a very specific set of conditions. Line of sight, open field, no obstructions, usually elevated off the ground to eliminate multipath reflections, antennas perfectly matched. Transmit power at maximum, no co-channel interference, and in most cases the two devices were on a lab bench connected to calibrated reference antennas that no real product will ever use. That is the number on the datasheet. That is the number in the marketing copy. That is not the number you will get. Now here is where it gets interesting. The range a BLE device achieves in the real world is not determined by one variable. It is determined by at least 6, and most of them are outside your control. Transmit power, receiver sensitivity, antenna gain, antenna placement, environmental path loss, and interference. The datasheet usually gives you the first one, sometimes the second, the rest are your problem. Transmit power is the obvious one. BLE operates in the 2.4 GHz band. Maximum transmit power under FCC Part 15 rules is 20 dBm, which is 100 milliwatts. Most commodity BLE chips ship at 0 dBm by default, which is 1 milliwatt. That is a factor of 100 difference in output power before you have touched a single line of code. A chip rated at 100 meters at 0 dBm will behave very differently at 10 dBm. This is not hidden, it is just never explained clearly. Receiver sensitivity is less discussed and far more important. This is the minimum signal level the chip can detect and successfully decode. It is measured in dBm and the numbers are negative. The more negative, the better. A typical BLE chip has receiver sensitivity around 90 dBm. A well-engineered one reaches 95 dBm. The Multinav Pro Plus BLE module uses a chip and RF front-end combination that achieves 104 dBm. That difference of 14 dBm between 90 and 104 is not a small margin. In free space path loss terms, 14 dBm translates directly to range, because every 6 dBm of sensitivity improvement roughly doubles your usable range. 14 dBm is more than a 2 times improvement. It is closer to 5. Now let's talk about antenna gain and placement. A chip antenna, which is what most modules use, including the Multinav Pro Plus, has a gain profile that is directional. It is not a perfect sphere, it has nulls. If you mount the module inside a carbon fiber frame, which blocks RF, and orient the antenna toward the ground, which adds absorption, you have just lost several dBm of effective gain from the geometry alone. None of this appears in any data sheet. The data sheet was written for a device sitting on a bench. Path loss is physics. At 2.4 GHz, free space path loss at 100 meters is approximately 80 dBm. At 1 kilometer it is approximately 100 dBm. At 5 kilometers it is approximately 116 dBm. At 20 kilometers it is approximately 128 dBm. These numbers are fixed. You cannot change them. What you can change is how much signal you start with and how sensitive your receiver is when that signal arrives. This is why the Multinav Pro Plus achieves the ranges it does. 20 dBm transmit power, 104 dBm receiver sensitivity. That is a link budget of 124 dBm before you account for antenna gain. At 20 kilometers with free space loss of 128 dBm, you are right on the edge of the physics, which is exactly where the numbers say you should be. The ground matters more than people realize. One of the most consistent range discrepancies in BLE testing is between ground level operation and elevated operation. When both devices are on the ground, multipath reflections of the surface create destructive interference that attenuates the signal. This is not a defect, it is geometry. When one device is elevated on a drone, on a tower, on a mast, those reflections largely disappear. This is why our ground-to-ground range is 5 kilometers, our man-to-drone range is 15 to 20 kilometers, and our drone-to-drone range reaches 50 kilometers. The physics does not change, the geometry does. The last variable is interference. The 2.4 GHz band is shared with Wi-Fi, Zigbee, microwave ovens, Bluetooth audio devices, and an increasing number of IoT sensors. In a dense urban environment, the noise floor on 2.4 GHz is measurably higher than in an open field. A device rated at 400 meters in a field may struggle to reach 50 meters in a warehouse. This is not a lie, it is a test condition that does not match your deployment environment. So, what should you actually look at when evaluating a BLE module? That is the physics behind every claimed range you have ever read and every real-world result that did not match it. Now let me show you the hardware we built once we understood what actually controls range. This is the range claim that holds up under actual physics. Up to 50 kilometers between two modules, 5 kilometers ground to ground, 15 to 20 kilometers man to drone. Those numbers come from a real link budget, not a bench test in a controlled room. 2 megabits per second is the data rate. Most discussions about BLE range ignore throughput entirely, but range without bandwidth is not useful for drone telemetry or real-time sensor feeds. This module delivers both simultaneously. The STM32WB B07CC V6 is the processing core. It manages the full BLE stack while leaving headroom for your application logic. This is not a radio chip bolted to a microcontroller. The stack and your firmware share one optimized silicon die. 57 by 47 millimeters. That is the full module footprint, including the 140 millimeter antenna. The fixing frame holes sit at 54 by 34 millimeters, designed for direct integration into drone frames, enclosures, and sensor housings without adapters. The interface connectors are not generic headers. They are purpose-designed for the GNSS module, the sensors module, and the motor and battery management module. Stack them and you have a complete autonomous system platform, not a collection of mismatched boards. The RFOXiA Connect app is the control layer, PS5-style controller interface, live GPS map, real-time sensor data, all operating over the BLE link with no internet connection required. The range of the app is the range of the module, up to 20 kilometers. BLE chat is what happens when the range problem is solved at the hardware level. Direct device-to-device text, voice, and data transmission with no towers, no infrastructure, no monthly bill, disaster response, remote field operations, off-grid coordination. Full source code access over SWD. Every pin, every register, every behavior is yours to modify. The module does not lock you into a firmware image. It gives you the hardware and gets out of your way. The RTC crystal provides timing accuracy that matters when you are synchronizing multiple nodes across a distributed network. Time-stamped sensor data, coordinated transmission windows, time-sensitive navigation applications all benefit from a precise onboard clock. Receiver sensitivity in dBm. The difference between them. This is your link budget and the test conditions under which the claimed range was measured. If the manufacturer does not tell you all four, the range claim is not a specification, it is a marketing aspiration. The reason nobody explains this clearly is not malice, it is that the chip manufacturers are writing for RF engineers who already know this, and the marketing teams are writing for builders who do not. The gap between those two audiences is where every confusing range claim lives.